clearance, the head of BMKG, Professor Dwi Glorita Karnawati, is not be able to join with us here. So thank you, Pak DM, for joining us in this occasion. Ladies and gentlemen, in attendance, the online group discussion event is about to commence. In order to maintain the order of DG and agenda, we kindly request participants to mute their microphone unless you want to talk or have a question. Participants are encouraged to activate their cameras using the provided virtual background, which can be found in the chat box. Maybe you can check your chat box to find the virtual backgrounds, and you can apply for this meeting. And thank you. Ladies and gentlemen, now we shall begin our online group discussion. The Honorable Deputy Head for Meteorology, Bapak Guswanto, the Honorable the Acting Head for Center for Aeronautical Meteorology, Bapak Hadi Subarkah Raharjo, the Honorable Head of Center for Public Meteorology and Marine Meteorology, Bapak Andri Ramdhani and Bapak Eko Prastyo, the Honorable Head of BMKG Regional Offices, the Honorable Official within the BMKG Headquarter Office, the Honorable Head of Meteorological Station of BMKG, and the esteemed speakers, Dr. Jarat Tenman and Mr. Kentaro Suboy, and our colleagues from Aviation Meteorology Division of Japan Meteorology Agency, and all the respected participants, ladies and gentlemen. Good morning, and it's been great honor for us to be here and welcome each of you to the online group discussion MetbangTalk 14 edition with the topic, the utilization of satellite data to provide aviation weather information. Ladies and gentlemen, in this opening, we have several items of our agenda. The first agenda is singing the national anthem of Indonesia, Indonesia Raya, followed by the BMKG anthem, Mars BMKG. Then we will be presented with a report on the online group discussion, MetbangTalk objective. Subsequently, we will listen to the opening remarks from the head of, from the deputy head of meteorology, and continuing the proceeding, we will engage with presentation delivered by speaker, followed by interactive discussion session. So, ladies and gentlemen, we will begin by singing the national anthem of Indonesia, Indonesia Raya, and followed by the BMKG anthem, Mars BMKG. We would like to invite all of the audiences to stand up while the songs are being performed. Thank you, and please kindly be seated. Ladies and gentlemen, let us start this event with a prayer, hoping for the success and great insight of this online group discussion, and that everything will run well without any obstacle. Pray based on our individual belief. The prayer is speaking. Done. Okay. Okay, distinguished participants, ladies and gentlemen, without any further ado, we would like to invite the acting head of aeronautical meteorology of BMKG, Bapak Ahadi, to deliver the OJD MetbangTalk objective. To Bapak Ahadi, the floor is yours.
Thank you, Mbak Reza. The Honorable Deputy Head for Meteorology of BMKG, Mr. Guswanto, MSI. The Honorable Head of Center for Public Meteorology and Marine Meteorology, Dr. Andri Ramdhani and Mr. Eko Prasetyo. Honorable Heads of BMKG Regional Office, the honorable official within the BMKG Headquarter Office, the Honorable Head of Meteorological Station of BMKG, the esteemed speaker, Dr. Gerard Denman and Mr. Kentaro Suboi, our colleagues from Aviation Meteorology Division of Japan Meteorology Agency, respected participants, ladies and gentlemen, good morning. Please allow me to deliver the objectives of online group discussion OJD MetbangTalk with the topic, the utilization of satellite data to provide aviation weather information. Meteorological satellites play a crucial role in aviation safety and efficiency by providing real-time data and weather forecasts. Therefore, weather satellites are recommended as one of the data sources by ICAO Annex 3 Meteorological Services for international air navigation. Access the real-time weather information assists pilots in making decisions based on data, enhance air traffic management, and ensure the safety and comfort of passenger and aircraft crew during flights. Although weather satellite technology has significantly advanced in recent decades, there are still some knowledge gaps and challenges related to the satellite data for aviation weather. Weather satellite primarily observe cloud cover, temperature, and humidity. However, certain aviation weather parameters such as turbulence and volcanic ash require specialized method of satellite data processing. In this regard, data processing algorithm needs to be continuously improved and integrated into the operational system. Over the past year, the Center for Aeronautical Meteorology has conducted online group discussion, namely MetbangTalk, in a monthly basis, bringing together operational staff from meteorological stations located at airports across the Indonesian region. The topic cover include aerodrome forecast and trend forecast production, encoding synoptic weather report, prediction of low-level wind shear using anemometer network and temporal convolutional network, meteorological services for air navigation, optimization of radio sonde data to support early weather warning, and then utilization of weather radar for trend forecast to enhance flight safety. In today's OJD, we are honored to have two experts from Bureau of Meteorology and Japan Meteorological Agency to share their insight about satellite application on observing and forecasting volcanic ash and other significant weather phenomena for aviation. Today's edition of MetbangTalk aims to first acquire knowledge regarding the last methods and best practices from experts at the regional and global level related to the use, interpretation, and processing of weather satellite data. And then the last one is enhance the abilities of observer and forecasting in utilizing satellite data for providing aviation meteorological information. Finally, I hope that today OGD will yield fruitful result, which will be advantageous to the advancements of high-resolution satellite application for improved forecast of aviation-related weather phenomena. Therefore, it will be very helpful for our operational staff operating in meteorological station across the nation. Thank you.
Thank you, Bapak Hadi, for the reports. And ladies and gentlemen, we are going to listen the opening remark from Deputy Head for Meteorology of BMKG, Bapak Guswanto. Bapak Guswanto, the time and floor is yours.
Thank you, Reza. Ladies and gentlemen, my name is Guswanto as Deputy for Meteorology at BMKG. Greeting from the head of BMKG, Prof. Dwi Korita Karnawati. She apologized for not being able to open this open group discussion forum because she has other urgent needs. Honorable Head of Center for Aeronautical Meteorology, Head of Center for Public Weather Service, Honorable Official within the BMKG Headquarters Office and Meteorology Station, our esteemed speaker, especially Dr. Jarat Denman, Volcanic Ash Advisory Center, Darwin, Bureau of Meteorology, and then Mr. Kentaro Suboy, Japan Meteorology Agency, from Japan Agency. Ladies and gentlemen. Ladies and gentlemen, all participants, a very good morning. On behalf of Indonesian Agency for Meteorology, Climatology, and Geophysics, it is my immense pleasure to welcome our speakers and all participants to the online group discussion. This monthly discussion serves as a knowledge-sharing platform among aeronautical, meteorological observer and forecaster across the Indonesia region. Our focus today is on a critical theme, the utilization of satellite data to provide aviation weather information, especially in Eastern Indonesia. This current edition of MetbangTalk is being held a part of series event of commemorate National Meteorology, Climatology, and Geophysics Day, which fall in 21st July every year. And also, this is for our Independence Day in 17 August. In this edition of MetbangTalk, we have the privilege of hosting our special speakers from two renowned institutions, the Bureau of Meteorology of Australia and Japan Meteorology Agency. The topic at hand differs into the technique and best practices for utilizing satellite data in monitoring and forecasting volcanic ash and other meteorological phenomena significant for aviation with significant impact for aviation safety. In this opportunity, I wish to express my gratitude to our speakers, Mr. Jarat Denman and Mr. Kentaro Suboy, for generously offering their time and insight. Ladies and gentlemen, all participants, BMKG as the national agency entrusted with meteorological, climatological, and geophysical services has been providing aviation weather services through our headquarters to meteorological world office and over 120 meteorological stations located at airports across Indonesia. The headquarters plays a role in disseminating significant weather information at a medium level, while the WMO offering the issues segment within the Jakarta and Ujung Pandang flight information region. Our meteorological station are tasked with essential aerodrome weather information, including METAR, staff, and aerodrome warning, and more. In complement the ground-based observation, satellites serve as substantial tools for the operational staff at BMKG. This satellite observation from the bedrock of our weather information, thus rendering our discussion today a valuable opportunity to learn from the expertise of our speakers. Certain region influenced by distinctive local factor like topography may exhibit unique weather behavior, further underlining the importance of providing accurate and real-time weather information for various sectors, including aviation. Equally important, in respect to the aviation safety, volcanic ash stand as a significant potential hazard, considering Indonesia's abundance volcanoes. Ladies and gentlemen, Mr. Dr. Jared Derman from the Volcanic Ash Center, Darwin at BOM, Australia, will share insight about the satellite application for volcanic ash detection and forecasting. Currently, Mr. Kentaro Sugoi from GMA will share about the role of Himawari 8 or 9 satellite product in shaping aviation meteorology understanding. In light of this matter, a pivotal objective of our endeavor with the field advancement of high-resolution satellite application to provide enhanced forecast for aviation weather phenomena. A notable illustration of our commitment to this pursuit can be observed in a specific context of Papua, Eastern Indonesia. Given its unique geographical feature and complex atmospheric condition, we are diligently work to elevate the accuracy of aviation weather information in this region. By leveraging high-resolution satellite data, we aspire to empower pilot, air traffic controller, and the other stakeholders with timely and detailed insight into weather pattern, turbulence potential, cloud formation, and other critical factors to significantly influence aviation operation. Ladies and gentlemen, I believe that expertise of speaker will greatly enrich discussion and create a valuable learning experience for all involved. Moreover, through this occasion, we are aiming to raise awareness among BMKG's operational staff and enhance our preparedness. Finally, I extend my appreciation to all participants, speakers, and support for their active engagement in this dynamic exchange of knowledge. I hope today's FGD MetbangTalk will be fruitful discussion forum between the speakers and participants. Thank you, and I wish you great today. Thank you very much.
Thank you very much, Pak Guswanto, for the wonderful remarks and the opening events. And so, ladies and gentlemen, this is our main agenda. We will proceed to, we will listen the presentation from our speakers, followed by discussion between the speaker and the participants. This session will be moderated by my colleague, Asria. So, Asria, now I will give the floor to you.
Okay, thanks, Reza, for the handover. I just wanted to confirm if everyone can hear me. Yes. Okay, thanks a lot. Right, the Honorable Deputy Head for Meteorology, Mr. Yuswanto, the Honorable Heads of Public Weather Center and Marine Meteorological Center of BMKG, Mr. Andri Ramdhani and Mr. Eko Prasetyo, the Honorable Acting Head of Center for Aviation Meteorology, Mr. Ahadi Subarkararjo, the Honorable Heads of BMKG Regional Offices, the Honorable Officials within the BMKG Headquarter Office, the Honorable Heads of Meteorological Stations of BMKG, our esteemed speakers, Dr. Jared Denman and Mr. Kentaro Suboy. And also hello to our colleagues from Aviation Weather Forecast Division of GMA. This morning we were just informed that we have more colleagues joining from GMA, so thanks a lot for that. And our respected participants, ladies and gentlemen, good morning. My name is Asria. I'll be the moderator of today's presentation and discussion session. The order of our agenda today consists of presentations from our two speakers, each lasting for around 20 minutes. But of course, our speakers are much welcome to do it a little bit more than 20 minutes. The first presentation will be from Dr. Jared Denman from the Bureau of Meteorology Australia, who will be presenting about the satellite applications for volcanic ash information. And the second presentation will be from Mr. Kentaro Suboy from Japan Meteorological Agency, who will be presenting about Himawari 8 and 9 satellite products for aviation weather. And following these presentations, we will have a question and answer session. I would really encourage the participants to actively engage in the discussion, especially considering the presence of our satellite experts here together with us. So please do ask as much as questions you have, as long as we have time, of course. All right, now before we proceed, I wanted to greet our speakers. Hello, Dr. Jared and Mr. Kentaro.
Hello.
Hello, how are you?
I'm well, thank you.
That's great, thanks a lot. Mr. Kentaro?
Yes, very good. Thank you.
Thanks a lot for confirmation. Now I'm going to introduce our speakers in today's online group discussion. The first speaker is, as everyone has already seen in the meeting, is Dr. Jared Denman. He's the manager of Volcanic Ash Advisory Center, or VAC, in Darwin, under the Bureau of Meteorology Australia. Dr. Jared completed his Bachelor in Space Science and Astrophysics in 2005 and completed honors in physics in 2006, though from the University of Adelaide. In the following stage, he went on to study high energy gamma rays and detection methods to support the design of a new gamma ray detector, and was awarded Doctor of Philosophy in Astrophysics in 2013 from the University of Adelaide. Dr. Jared became a public servant in 2013, where he used remote sensing and satellite imagery to support projects. He later moved to VAC Darwin in the Bureau of Meteorology in 2015 as a volcanic ash forecaster and gained years of experience working with different satellite imagery to analyze many different eruptions. Dr. Jared transferred into VAC Darwin manager role at the end of 2018, where he has been able to share his experiences with his forecasters, also interacted with international counterparts to support the alignment of services, as well as discuss the volcanic ash sciences and satellite techniques with other VACs and WMO to improve their monitoring capability in the VAC Darwin. He also represents Australia on a wide number of ICAO and WMO groups to improve the volcanic ash science and services. And our second speaker is Mr. Kentaro Suboy. He's from Japan Meteorological Agency. He had a background in Masters of Electrical Engineering from Waseda University. Mr. Kentaro became a government officer in Japan Meteorological Agency in 2005. In the following 2 years, he started in the aviation weather observation in Chubu Centrair International Airport. And from 2007 until 2012, he is in charge in the Domestic Meteorological Data and System Management Division. And on 2012 until 2023, Mr. Kentaro worked in the international meteorological data and system management. Mr. Kentaro worked for the ICAO, SWIM, and IOXM implementation in the working group. So for those who are not familiar with this yet, this is about the transition from the traditional alphanumeric code of operational meteorological data to the graphical format. And also he's actively participating in the WMO information system or WIS in some expert teams. And from 2023 up to this time, he is in charge in the international coordination in the Office of Aviation Weather Forecasting. All right, now we are already familiar with our speakers. Now I would like to invite our first speaker, Dr. Jared Denman. I will give the floor to you and time's yours.
Thank you, Astria. I will share my screen.
Sure.
Let me just get the screen up. Can you see my screen?
Yes, I see the full screen now. Thanks.
Okay. Okay. Thank you. I think my system is lagging a little bit, so I will turn my camera off. So hopefully it goes smoothly because I've got a few videos in this presentation. So thank you for inviting me to speak to everyone today about the usage of satellite imagery at VAC Darwin for monitoring, detection and identification of volcanic ash. So I'll start off with just talking about some satellite data. So VAC Darwin uses geostationary satellite imagery, polar orbiting satellite imagery, and SO2 sensors. The primary data comes from geostationary satellites. So in this case, it's from Himawari 9, provided by JMA. So Himawari 9 has 16 bands as shown on the right. The first three are used to create visible imagery. The next 3 are for infrared, and then the last 10 bands are the IR bands. Some of the bands are higher resolution, especially the visible bands, and the imagery comes in every 10 minutes. So next on the list, we have some of the polar orbiters that we use. So we use the National Oceanic and Atmospheric Administration, so NOAA's advanced, very high resolution radiometer. Imagery is not used as much from that one now, but we do use a lot more from Aqua and Terra, so the moderate resolution imagery spectroradiometer, so MODIS. It's got 2 sensors there, so Terra launched in '99 and Aqua that was launched in 2002. Because they're polar orbiters, you don't get a lot of imagery over the area compared to geostationary, so it's just nice to have backup imagery to support your monitoring. And lastly, we use a lot of SO2 sensors at VAC Darwin. We typically use OMI and AIRS sensors, which provide us with an overview of where there could be potentially sulfur dioxide in the area. So VAC Darwin uses many of the same by Himawari 9. So we pair this with scientific needs. We have multiple images of plastic used during an identification of volcanic gas. So the technique that we typically use is pattern recognition, SPADO, and RGB composite image. Just image alone is not necessarily going to give you 100% confirmation of a volcanic ash eruption or an ash cloud. So evidence is usually paired with other support. Allows back forecast to determine what is seen on the imagery and is eruption. So supporting information usually support, ground reports, volcano imagery notice for aviation, pipe reports, lightning data, sulfur dioxide detection detection. Sometimes the clear on satellite imagery that an eruption may take place. So for in 2017, you can see as we transition into times of the visible imagery, you can see conditions, minor eruption happening that kind of move multiple frames. In that case, probably I think that we can look at that's an eruption. But when there's a lot of meteorological in the area, they need information to help them techniques. So I'll start just mentioning on the visible and true color imagery. So the first bands from Himawari 9, the first 3 bands used to create visible imagery. It's only during the day and it's higher resolution than the near infrared bands and IR. It can be used to create true color imagery, which is a better representation of the ash cloud, especially when it might appear gray or brown. We use for true color imagery, your MODIS imagery from Terra and Aqua is usually true color. So you can see the top image, a loop of Dakota with the plume moving out to the southwest. Based on Himawari. Bottom image is MODIS imagery. I believe that one could be Terra. But you can see with true color, you can actually identify the meteorological cloud is quite white. So that's why true color imagery is good to help identify. I also mentioned that the image is useful to identify something that is like ash. You can look at the brightness temperature to gain the height of the ash cloud and compare that to numerical models. So the first technique that I wanted to go through is pattern recognition. So it's the most common technique used by Vac Darwin for detecting volcanic ash clouds, as many of the enhancements can also be affected by tropical weather. So using unenhanced satellite imagery, so usually the true color and visible imagery, you use pattern recognition techniques to rely on the recognition of visual differences between what we see as a volcanic ash cloud or potential volcanic ash cloud and meteorological cloud. However, detecting a volcanic ash eruption on satellite imagery can be difficult when there's a lot of meteorological cloud in the area. So how do we use pattern recognition? What are we looking for? So we look for a line or a plume extending or that's anchored to a volcano that doesn't appear to move over the top. We're also looking at discoloration on true color imagery. So you can see the top image here was Rinjani 2015. You can still see a brown gray colored signature, but it's anchored to the volcano. So it's continually coming from that single point. Similar with the Sangianapi eruption in 2014, but with the true color, you can see the difference in color signatures from it. So if you're lucky enough to get a pass from the polar orbiters, it's quite high resolution and it's really good for supporting that identification. So the other one that we have there is cloud formation that is inconsistent with north diurnal vective times. We're expecting in the afternoon storm activity to appear or cloud formation in the area. If development of a cloud or a volcano is sync, then that would potentially be a volcanic ash cloud. So in that case, you're looking for differences in meteorology expecting. So you do actually have to be a little bit careful. In India, the loop is actually for Hungatai eruption eruption in Tonga 2022 January. That one actually went to, I think it was 53 kilometers into the area, which was 190,000 feet, so quite high. That's eruption you can see quickly over the volcano, and then start moving across to the west. So it's quite, but moving in the direction everything is around the area. Probably in that expecting cloud, that was an easier eruption to pick up. If we look at the bottom cloud in the area, it's a persistent overshooting top or persistent feature that's not moving the mineral cloud. Very when the eruption happens, split second, 3 years, and the eruption has one is very difficult to pick up. Satellite alone is not 100% confirmation that an eruption. So the next one we'll go through quickly is the near infrared imagery. So it's very useful for identifying thermal anomalies or hotspots at volcanoes, especially in the 3.9. It's very useful to help separate ash and ice, especially during the day, if you use a slightly lower band. So I think the 1.6 micron band. Near infrared can be used in some false color imagery, which we'll go through in a moment. When it does pick up a thermal anomaly or a hotspot, it can represent that the activity at the volcano, such as lava fountaining or minor lava emissions. So we've got a couple of examples here. So at the top, we have the thermal anomaly spot for Manam in Papua New Guinea. It was appearing on the infrared. Doesn't appear in the IR, but it appears in the 2 false color images that we've produced that use the 3.9 micron band. Whereas you do have to be a little bit careful with thermal anomalies because a bushfire can also be confused with a potential activity at a volcano. So down here we actually have image of which one was this one? Can't remember the volcano, but it was in Indonesia, and it was confirmed that there was a little fire next to the volcano. So it wasn't actually the volcano that was active, because this one hadn't been active in thousands of years. It was a fire that was actually happening in the area. So a confirmation, a quick message to the ground observatory cleared up that no, the volcano was not active. It was a bushfire in the area. And I know that's something that this imagery is useful for detecting fires. So I know at the Bureau of Meteorology, the bushfire sections, they look for some of these thermal anomalies and use a lot of this with their forecasting as well. So the next technique that we'll go through is split window. So it's differential absorption. So radiation that's received by satellite, it depends on the amount of absorption or scattering by the clouds. Transparent volcanic ash clouds, they absorb and scatter ground emitted radiation more strongly than 11 micron. So this line here, we see the volcanic ash at the top here, this point, compared to ice/water rich clouds that absorb and scatter ground emitted radiation better at 12 microns. So if we compare this one up here, so we can just see there's a bit of separation between them that we can kind of utilize. So this, we look at the brightness methods and the absorption between the 2 bands to help separate between them. So you can actually then subtract one from the other and then try and highlight the particles that more represent volcanic ash. So there are limitations around this technique. So it only works for a semi-transparent cloud. So at the start of an eruption, so we saw on a couple of those bigger eruptions, so the Hunga Tonga event, that one would have been a very thick volcanic ash cloud, so not likely to show an ash signal from this technique. The results can be reversed if the surface of the cloud, so the land, surface below the cloud, sorry, so the land or sea or underlying cloud is cooler, then it can have it can interact with what you're seeing. Very cold cloud tops or incorrect IR channels can sometimes produce false alarms. Things are misaligned, or if there's high water vapor and ice content within the ash cloud, it can reduce the effectiveness of the technique. And that's a typical problem in the tropics, especially when the eruption goes quite high, quite quickly. You might get ash there, but it automatically kind of is encased in ice, so it freezes quite quickly, so it can distort the signals that you're expecting from split window technique. So here, the top image, we have just an eruption for Manam in Papua New Guinea. You can see that the white section here is actually glaciated ice. So this component went quite high in the atmosphere quite quickly. So we know it's from the eruption because it was traced back to the volcano. And you've got the low level plume. So looking at some of the IR bands themselves, you can see that the plume had a signal in it, which would represent ash, which would be seen here, but the high level component is quite bright, so it's confused it with ice and water when it actually is ash. So pairing these techniques together can actually help you separate and look at some of those difficult cases. The last technique is the false color RGB image. So it uses the split window technique, but it actually kind of reverses it. So you want the ash signal to be bright, so it still uses the 11 and 12 micron bands, but I believe you have the 12 micron band subtracted by the 11 micron band to pass through red channel. So this example here is for Raung in Indonesia. So the top one here is the window, but flipped. So volcanic ash will appear bright red. The green channel is actually comparing SO2 absorption. So in this case, it's the 8.5 microns. It's not, so it appears bright green in the false color imagery. And then blue is just an IR band to contrast for the background. So RGB imagery can be used to highlight different things depending on what band you pass through each of the, what infrared bands you have to pass through the colors. So it could be used for ash, SO2, dust, gases. So the result image is the one here in the bottom right. See the pink picture here for volcanic ash and the very green for sulfur dioxide. So I'll go through another example, but also false color imagery does suffer from the same drawbacks. Since it does use the same channels as split window, if the ash or SO2 is embedded in ice and water, then it can be difficult to separate out and get those signatures that you're expecting. So if you're expecting a bright pink signature or a bright green signature, split window can sometimes not be as useful when the eruption goes very high, because it could be contaminated with ice, or it could be the volcanic ash cloud is too thick. So we use the RGB signatures, but pair that with pattern recognition, but also effective tracking of that feature back to the volcano or from the volcano. So in this example here, we have an eruption from Mount Sinabung in on the 19th of February 2018. So I've got here hourly time step starting at 02, 03, 04, and 05. We have visible imagery. We have the RGB imagery using the thermal band, so 3.9, and then we have an RGB using the 8.5 band to highlight SO2. You can see from the first image that there's separation between, because the eruption is quite small but also thick, there's not much separation between volcanic ash and SO2. In the next hour, you can see that as the cloud grows and starts to dissipate, you are getting some of the pink signature appearing for volcanic ash and some of the bright green for gases. Then as you step through again and again, in the time steps, you're starting to see this separate out a lot more because the cloud has now become semi-transparent. So we're getting the ground emitted radiation coming back and absorbed, scattered through the cloud, coming up to the sensor. In this case, we can see something I wanted to point out is this dark red, kind of black signature that's appearing here. It is actually volcanic ash, but it's most likely that this part of the volcanic ash is encased in ice. So it's not giving you your typical volcanic ash signature. You're getting something that's a bit of ash, a bit of ice. So we know it from the volcano because look at the imagery in the imagery loops. So the animations, you can actually trace it back to the volcano. So we know it's come from the volcano, and the split window seems for lower altitude. So you can see the bright pink signatures at slightly lower levels, same with the SO2, but at higher level, it can be a bit mixed with ice. So you need to be careful when you're doing your analysis. Just another example here for Merapi. It was this year in March. This one here, because there's cloud in the area, it was a little bit more difficult to pick up, but you can see there's a little bit of darker reds, brighter pink signature here on some of the false color imagery, especially the one that's picking up some SO2. So there's kind of a little bit of an ash signal in that. So we don't just use a single image to monitor and detect for volcanic ash. We use, 6, 7, 8 different images to try and isolate what is volcanic ash before it goes into our volcanic ash products. So this one here is just an image for Dacono, Mount Dacono. We can see the ash plume. So in this case, it's anchored to the volcano. So we knew that that was an ash cloud based on the animated imagery. But you can see you're getting a signature in the false color image, which highlights that it is volcanic ash that we're looking at. So this technique is very good for lower level activity as well. But because you may see it visible imagery, sometimes because the IR imagery is slightly lower resolution, you may not detect it on your false color images. Again, it's just trying to pair it with as many different images as possible to confirm that it is an eruption. And in the case that we have here is for Dacono and Ibu. In this case, there's a very strong signature of volcanic ash at Mount Ibu. It's very hard to see, but there is a bit of a thermal anomaly also underneath the volcano and the ash cloud that's there. So this is just a good case of this signature. So you're looking for this bright reddish pink signature here in your false color images. And just to really highlight some of the differences. So this was the top here is the Hunga Tonga Hunga Ha'apai eruption in 2022. After the eruption, there was really no difference between what we were seeing on satellite imagery because that cloud was so thick that split window wasn't working and wasn't separating out volcanic ash and gases. Similarly, with the Ulawun eruption in Papua New Guinea in 2019, you can see at this part here, in this one, you can start to see sulfur dioxide appearing, but there wasn't any strong volcanic ash signal. Whereas the Agung eruption in 2019, it was slightly lower. You can see a very strong signature for volcanic ash appearing there in our false color imagery. So split window was working quite well in that eruption. So sometimes with satellite imagery, you can't get the confirmation that, that is an eruption. So you look for other supporting information. So one thing that you can look at is sulfur dioxide. It can be used as a precursor for a volcanic eruption or general degassing from the volcano. It can also be used to help track where volcanic ash could be heading. However, as the ash cloud moves and dissipates, the ash and SO2 separate differently due to different particle sizes. So different interactions with the atmosphere, and they disperse differently. So after a while, the SO2 may not indicate that there's any ash there, but it could just mean that an eruption has taken place. So maybe trace back where the SO2 has come from to confirm if there was an eruption or not. So this one here is just an image from the OMI sensor. See the Manama in Papua New Guinea was very strong SO2 signature, which actually paired with a large eruption that we had an advisory out for. The false color imagery can also be used to help highlight SO2 if you're looking at the 8.5 micron channel from Himawari 9. Because they are polar orbiters, they don't always, you don't always have a correct pass at the time of the eruption. So sometimes it could be a little bit hit and miss as to if it detects any SO2 from an eruption. Other supporting information could be lightning data. So lightning data is quite useful. Most eruptions produce lightning associated with the charged particles in the ash column. So the volume of lightning depends on the size of the eruption. Sometimes it's useful, and sometimes it's less useful in smaller eruptions, but it's very useful in a very large eruption. So when you consider lightning over a volcano, you need to consider the current weather situations and if lightning or a thunderstorm is expected in the area, or does the activity seem out of place? For large eruptions, there are long-lived sustained eruptions. The lightning will be stationary over the volcano compared to the other activity in the area. For shorter eruptions, it could be stationary for the length of the eruption and then move away, which could also look very much like a thunderstorm developing. So the two examples here, the one on the left is for Hunga Tonga, Hunga Hai Apai in Tonga. So that eruption, as I mentioned before, was to 53 kilometers in the atmosphere. So according to lightning networks in the area, there was 400,000 lightning strikes for this eruption, and there was 200,000 lightning strikes during an period of an hour when the eruption started. The second example was slightly smaller, so it was only 63,000 feet. So the other one was 190,000 feet. This was 63,000 feet, but you can still see there was lightning associated over the volcano with this eruption. So it was something else to help, I guess, confirm that there was an eruption occurring. Next, we have the other supporting information, which comes from the state volcano observatories. So the volcanic activity reports, the volcano observatory notice for aviation. So those are very useful to pair with something seen on satellite imagery. We use the WhatsApp chat and webcams and YouTube to help watch for early detection. of volcanic ash eruptions, the reports that we get from the MWO to say that they've had a report or seen an eruption, plus also pilot reports from airlines. So pairing all of those supporting information, so the reports here, lightning data, SO2, paired with satellite imagery, then you should be able to detect most of the volcanic activity in the area. If there's too much meteorological cloud in the area, you may get some of that information, or if the volcano is too remote, sometimes it can be very difficult, and satellite imagery may be your only reporting tool. So I'll just quickly finish up here, the last slide. So obviously, once we've detected the volcanic ash cloud and we've determined the height, that information of start time, height, volcano location, that information then all goes into our dispersion models. So we have dispersion ensemble prediction system, so DEPS. It's an ensemble-based dispersion modeling system, so it uses 32 NWP models to provide a probabilistic output of where the ash could be moving. So then the forecaster will use the satellite observations, the forecasts, they'll compare it to what's happening with the NWP and the directions. All that information then goes into the forecaster generating their forecast for the volcanic ash advisory and graphic. So a lot of our information for forecasts come from dispersion modeling. And for some of the smaller eruptions, it's based on wind directions and speed from NW. And I will leave it there. So thank you, Tara McCarthy. Thank you everyone for allowing me to present today. I'll turn my video back on.
All right, thanks a lot, Jared, for your comprehensive presentation. Though I received some messages from the participants that your voice were sometimes laggy, especially when you showed animated pictures, but that's all fine because your presentation slides itself are already very clear. And once again, thank you so much. I also already saw some people posting their questions in the chat box, but I will go with them later on after Mr. Kantaro's presentation. And now I would like to invite our second speaker, Mr. Kantaro Suboy. I will give the floor to you. Time's yours.
Okay, thank you. And I'll prepare my presentation. So please wait for a while. I'll share my screen. Okay, can you see my screen presentation?
Yes, it's perfect.
Okay, thank you very much. So, okay, so I'm Kentaro Tsuboi from Japan Meteorological Agency, and Ashria already introduced me my career, and so before the presentation, my presentation, so I would like to add my personal career to visit Indonesia. I've been to Indonesia 3 times. So one is my honeymoon with my wife to visit Bali Island 2009. And the second one is Jakarta 2012. And also third one is Jakarta 2015. So because of my sister, elderly sister, worked for 2 years and also 3 years something. So to worked in Jakarta. So I visited her. So I enjoyed Indonesia culture and cuisine and many things. So visited, so I think it's a Taman Safari Zoo and Taman Mini. It's a very special park. It's Indonesia into one place. Yeah, okay. Thank you for your time. So let's get started my presentation. So it's JMS Himawari 8 and 9 satellite products for aviation weather. So actually, so I've moved to this position in Office of Aviation Weather Forecasting in this April. So before that, so I worked for ICAO and WMO for the information technology. It's a very bit different, but I worked for ICAO for a long time. So this chart is a tropical cyclone Mauer on 25th May this year. So it's a very clear. Himawari caught this tropical cyclone center very clear, and it is a case of the Himawari function. So this is a history of Japanese Himawari satellite. It's a brief overview of the Himawari series history. The Himawari named the first geostationary meteorological satellite. It's abbreviated to the as GMS. Series began its observation mission in 1978. It's the first. So Himawari in Japanese means sunflower in English. So the sunflower is very popular in Japan in summer in this season. So the GMS series was operated until number 5 by maybe 1995, and then JMA followed GOES 9, owned by the National Oceanic and Atmospheric Administration. You well known as NOAA, USA. JMA operated it under the name Pacific GOES from 2003 to 2005. So the multifunctional transport satellite, we call MTSat, is a series which performs both meteorological observation and air traffic control, was in operation from 2005 to 2012, 15. JMA changed the satellite name to Himawari in 2015. And Himawari 8 and 9 have been used in twin satellite operations to conduct stable and continuous observation since then. In addition, Himawari 8 was replaced with Himawari 9 as the operational system on December 13th, 2022, this one. And the next Himawari is now being in production, and it will come with a sensor that measures the amount of water vapor in the atmosphere called a hyperspectral infrared sounder. That's a 2029, next generation of Himawari 10. So next is a Himawari 8 and 9 specification overview. And Himawari 8 and 9 have the same design and carry an imager called Advanced Himawari Imager, AHI. The table on the right shows the arrangement of AHI spectral bands. AHI has 16 observation bands, including 3 for visible, 3 for near infrared, and 10 for infrared. And AHI is almost the same as Advanced Baseline Imager, ABI, which is carried on the GOES R series and satellites, with the exception that AHI has a visible band around 0.51 micrometer, and the near infrared band around 1.38 micrometer. Yep. The spatial resolutions of each band are 0.5 to 1 kilometer for visible bands and 1 to 2 kilometer for near infrared and infrared bands. And P2 is effective for monitoring aerosols, and it is possible to create an image that closely resembles the colors seen by the naked eyes by combining 3 visible bands. Next slide is AHI observations mode. And Himawari 8 and 9 are located at 140.7 degrees east on the equator. And AHI observes this area, which includes the Western Pacific, Southeast Asian countries, and Australia. Full disk observations are made every 10 minutes. Along with full disk observation, AHI also observes certain regions such as the whole of Japan, and a specific region that is set based on the objective every 2.5 minutes. And in addition to them, AHI can also 30 seconds, this one, observations of 2 regions. These are often used for positioning calibration, but can be set according to the situation, such as monitoring the development of cumulonimbus clouds. So why do we need the multiple spectral bands? So as I introduced earlier, AHI has 16 spectral bands. Each of the bands has different physical properties due to the difference of their center wavelengths. So by combining multiple images, we can monitor various phenomena and create analytical products. Here are some examples. As you can see, we can monitor diffusion of SO2 gas from last year's Mauna Loa eruption at this Sphinx area. It is already so Dr. Gerard Denman produced at volcanic ash. So we can, JMA provided many RGB or something products to identify the characteristics of phenomena. So next is JMA's Himawari products for aviation weather. So there are some products for aviation. JMA provides various Himawari products and to support safe operation of aircraft by utilizing Himawari images. So I will briefly introduce them. Some products. So it's now one product, clear air turbulence potential analysis is under development. So first one is convective cloud information, CCI product. Convective cloud information product aims to detect signs of rapid development of cumulus clouds by high-frequency satellite cloud observations. This product identifies 3 areas related to convective clouds: rapidly developing cumulus area, RDCA, and cumulonimbus area, CBA, and mid-low cloud unknown area, MLUA. It's provided every 10 minutes. And elements of CCI product, 3 elements that consist CCI product: RGCA is a cloud area which could potentially evolve into air mass thunderstorm within an hour. By using logistic regression analysis, the relation between Himawari images and the lightning observation is calculated in advance. And the highlighting probability area are detected as RDCA based on the current Himawari images. And CBA is vertically developing thick clouds, an area that seems to be overshooting. MLUA is an area covered by high clouds and the satellite cannot see below. In determining CBA and MLUA, we first extract thick clouds from Himawari observation data and the result of radiative transfer calculations using numerical weather prediction data as input, and then identify CBA and MLUA using the thresholds. So next product is CB Nowcast. CB Nowcast provides the estimated future CB area up to 4 hours ahead every 10 minutes using CCI products. Elements are high probability area of CB and its cloud top height, but it is under planning. JMA has provided CB Nowcast on the support website for SIGMET issue coordination on a trial basis since 19th June 2023, this year. It's a new product for SIGMET coordination. So next product is satellite cloud information chart. In this chart, it consists of the large scale CB areas, cloud top height, and cloud moving vector of upper cloud obtained by analyzing the Himawari images. The northern and southern hemisphere of the Himawari observation area are drawn every 30 minutes respectively. This is a large product that has been provided since legacy product that has been provided since 1995. But some airlines continue to use it for weather briefing prior to flights due to its simplicity. A major update was made to adjust to Himawari 8 and 9 observation data in 2019. Okay. So next product is fog detection product. In Japanese airport, traffic is sometimes disrupted by fog. So fog detection product provides the estimate to surface fog distribution day and night every 5 minutes. Only satellite observation doesn't identify fog and low clouds effectively. To address this issue, and the fog detection product uses numerical weather prediction data in addition to Himawari observations. This makes it possible to extract higher probability area of fog. So next one is ASH RGB. So nighttime detection of volcanic ash and SO2 gases. ASH RGB composite imagery uses channels that react to components of volcanic ash and volcanic gases. So high probability area of volcanic ash and gases it is detected, and it's a color and interpretation of the chart. So this is a case of the eruption of Mount Sibelchi Lucia, 10th April 2023 this year, and maybe so volcano is around there, and first it's moved to the west, and after that it's moved to the southwest and southeast. This is so mixed volcanic ash and SO2 gases plume. It's detected by the ash RGB. Okay, so last product is a clear air turbulence potential analysis. We are trying to develop the clear air turbulence potential detection product from Himawari images, applying a high-pass filter to the water vapor image and some gravity waves in the upper troposphere can be seen. Yep. So we aim to estimate the probability of experiencing clear air turbulence by neural network, which learned by pattern of these gravity waves. The figure on the left shows the sample data, and the cat potential area is estimated similar to this yellow area analyzed by forecaster. Now it's under development. So that's all the our product for aviation weather. It's a very not all the products from JMA. So next one is aviation weather info provision system, METRIA, and it is domestic aviation users can access various weather products provided by JMA from this website named METRIA. So you can get not only a Himawari product, but also METRIA radar data or a lot of information from this portal site. Okay. Next is a support website for SIGMET coordination. So JMA provides a support website to MWOs, meteorological watch office. It have to issue the SIGMET, including BMKZ for SIGMET coordination. SIGMET issuance for significant weather phenomena such as thunderstorms, turbulence, icing, tropical cyclone, and volcanic ash, affecting over multiple FIRs, requires communication between relating MWOs in advance. And support website provides online chat function to communicate with relating MWOs easily and quickly. You can monitor CCI products and numerical weather prediction data overlaid on SIGMET polygons, in addition to Himawari images to support SIGMET coordination activity. Yes, so last one is an example, is a support website. This one is last night, example for around the Indonesia. So Ujung Pandang FIR and Jakarta FIR. And polygon indicate so some SIGMET, WS SIGMET, and also there is a volcanic ash for WV SIGMET. So it's a little bit small one. It's issued by Indonesia. So WVID 21 is SIGMET. Next one is a WS SIGMET. First one is this one is icing. It indicates forecast area for this one, blue one. And also there is WS SIGMET for TS, thunderstorm. it's a red areas. Okay, last one is it's a Japanese. So yes, today, so tropical cyclone is now passing over Japan. So it's a western and mid part of Japan. So now passing over, moving north. And also, so last night, so we issued the TC SIGMET, and it's an additional example. But so support website can display the many information relating to Himawari products and the numerical weather prediction data, and also SIGMET. And it is used for users, MWOs, to coordinate with relating MWOs. Okay. Okay, that's all my presentation. That's it. Terima kasih. Thank you for listening. Any questions?
Thank you very much, Mr. Kentaro, for your comprehensive presentation. And also, I was even surprised that you had actually visited Indonesia way before I joined BMKG. And we're looking forward to meet you again in the future in Indonesia. Right. So now I would like to open the floor to the participants. If you have any question, please feel free to raise your hand or open your microphone. And also, if you are more comfortable to ask questions in Indonesia, I can also pass the questions to the speakers if you like. While waiting for the raised hands, I think I would go with the questions that are already posted in the chat. The first question is from Richard. He addressed this question to Jared. It is regarding the comparison between the distribution of volcanic ash from Himawari 9 and MODIS. And also regarding the identification method of the satellite image, so the color separation and stuff. And the last question, I think it was already shown in a few of your slides, Jared. Richard was wondering about the separation, like how to separate the rain clouds and volcanic ash based on satellite data. Jared, do you mind to answer the first three questions? Yeah.
Yeah, thank you for that, for those questions. I've been writing notes here. I've been reviewing the questions as well. So for the first one, we have looked at the distribution of volcanic ash with Himawari 9 and MODIS, or Himawari 8, because we did this in the past. Satellites, there is some slight difference in resolution. Sometimes one can show a slightly larger area, so it might have a finer resolution or slightly larger. So there can be some slight differences between them, but mostly they're pretty good for the main area where volcanic ash is located. And sometimes it can be difficult to compare MODIS with Himawari because MODIS is polar orbiting, so you usually only get one image over the volcano, maybe one from Terra and one from Aqua, so you've only got two to compare it with. Whereas Himawari 9, you have 10-minute imagery, so it's much easier to track and follow volcanic ash on Himawari 9. But usually when you compare them, you can kind of see a bit more of the features on MODIS. So the area is usually pretty good between the two satellites because it's just detecting volcanic ash. It comes down to resolution. It can be difficult to determine volcanic ash from satellite imagery alone. So for the second question, that's why we use supporting information, such as ground reports, webcams, lightning data, SO2, to help build enough evidence that the cloud is volcanic ash or it's a potential volcanic ash cloud. So we have at the VAC what we class as an evidence kind of checklist. So satellite imagery provides a lot of that evidence, but if the volcano is on, say, an aviation color code of orange, that might be a bit of evidence to say it's had activity, or it could be expected to have activity. A potential ground report, a pilot report, something suspicious, that adds up to help us. And then you can usually track the features. So if you're tracking something from the volcano, you always start your loops at the beginning of the eruption, and then you run it out so that you can follow every feature of what was come from the volcano if it's volcanic ash. So we usually, run long loops to keep tracking that cloud as it moves away. And yes, it is very difficult to detect volcanic ash clouds when it's covered by rain and not visible. We know other areas sometimes rely on LiDAR at airports. So I know BMKG has some LiDAR and information at airports that can also help under cloud. So we'd like to, I guess, work with BMKG on that. But then other than that, we rely heavily on the ground reports, pilot reports, and our dispersion modeling. If we get a ground report that says ash could be at a certain height, but we can't see it, we might, run some dispersion models and put that out. So if we've got an advisory out, for example, we might use dispersion models to continue predicting where that's going to go and have an estimated cloud to say it's estimated, we can't see it, but we know there's an eruption going on.
Thanks a lot for the answers. I believe Jared has already provided sufficient answers to Richard's question, so I will move to the second question from Maulana Sunu Pratama. This question looks pretty related with the previous questions, I believe. So he's wondering about other tools that might be required in case you want to determine the height and thickness of the volcanic ash dispersion, apart from the satellite data.
Yep. So satellite is really good at determining the height of an ash cloud if it's clear, if you've got IR imagery that shows the cloud developing. You can use the brightness temperature. So looking at the IR channels and finding the coldest component within that ash cloud, you can then compare it to your atmospheric profiles, your soundings, so your numerical model data, and then looking at where the height based on that temperature is compared to that atmospheric profile. It gives you an estimation of the height of the ash cloud, and it's usually pretty good if you've got a good signal on satellite imagery. Even the movement, you can help determine the ash cloud height based on the movement if it matches the winds at a certain height compared to some other areas that might say if the wind, if it's at flight level 200, for example, and the wind is suggesting east, but you see the ash cloud moving west, then it's like it must not be flight level 200. So you compare it to the other directions. In terms of height, that one is sorry, not height. Thickness can be difficult. You do probably need something else like maybe LiDAR, ground-based or satellite-based LiDAR can help with thickness. And even as the ash cloud moves from the volcano, based on its movement, if there's different winds in the atmospheric profile above the volcano, the ash cloud may move in different directions. So as soon as you start seeing it separate, you kind of have an idea that the base of the cloud could be at this height where the winds are moving in that direction because it's different to where the rest of the ash cloud is moving. So that kind of can give you a bit of an indication as well, but it is a difficult one. And it's something that as a group of 9 VACs, we are looking at, how we can easily determine that for the next kind of volcanic ash service. So yeah, thank you for the question, but definitely need something else other than just satellite imagery.
Thanks for enlightening, Jared. And I'm moving to, because we have like a bunch of questions here, so I'm gonna just read them out. The next question is from Muhammad Arif Munandar. In total, he has, there is for A, for B here, so in total 7. I think I will read out the first 3 questions. The first one is regarding the validation, field validation for the accuracy of the volcanic ash cloud detection. The second one is about the detection method of volcanic ash, which is maybe persisting far from the mountain, and also the recipe for the RGB used in the VAC. Dorian.
Yep. So thanks for those questions. We do verification of some of our forecasts. So it's very difficult to do field validation because once the ash is no longer there, it's very difficult to compare what your volcanic ash advisory was compared to where the cloud was. So we try and do that based on our forecast tools. So our forecast tools are dispersion models. We try and compare the accuracy of our forecast tools based on what we see on the data, so the imagery. That's how we do our verification and look at the accuracy of our ash cloud. So we try and do that and look at the observation and then our 6-hour forecast. And then in 6 hours, we can look at the forecast that we had versus the new observation and just see how well our dispersion models are actually working. So that's kind of how we look at the accuracy of some of the ash clouds and the observations, which is very similar to what other VACs do as well. In terms of detecting volcanic ash far from the volcano, you obviously will continue to track that cloud. So using your imagery loops and your signatures that you might get on your false color images, so your RGB images, and just continuing to track that feature. So if you know there's a feature that's volcanic ash, you go back, you do a loop from the start of it, and then you keep tracking it. And every time you get more imagery, you can create longer animation or loop to make sure you track that feature. So it's difficult, especially as it starts to dissipate and the signal gets weaker. But then once it's weak enough that you can't see it anymore, you cancel your product. So yeah, just that tracking of the feature and going back to the start of the eruption to make sure that you don't miss anything. The next part of the question was we can definitely discuss and share some of the bands that we use. I know there's also some information on the NOAA website about the imagery bands that the US use. So there's definitely more maps that you guys can create to support your efforts. And I saw the other presentation as well, that there's another other imagery bands that might be useful from JMA to provide. So definitely, I think between the two of us, we might be able to provide some different bands that you guys can create new imagery.
Yeah, that'll be great.
I think
Or
there was a
maybe
few more questions as well
yeah.
in that section.
Okay.
Yeah.
Can
So how do
you read
you
that?
determine low? Yes, I can read them. How do you determine low level and high level VA? So it's based on the height of the eruption. So using your brightness temperature in your infrared band, so your IR band, you can actually determine the height of the ash cloud based on how cold it is compared to atmospheric models. And then that will give you the indication of how high and how low, or how low the ash cloud is. That's usually how we determine the height of them. It's a really quick method, and then you can keep testing that, I guess, as the ash cloud moves and dissipates. You just have to be careful that as the ash cloud gets thinner, you may not get a good IR temperature reading from it. So you need to, continue at the height of the ash cloud at the start of the eruption. It usually will kind of move and maybe dissipate, drop a little bit. So just being mindful of that. What is the limit of high level and low level in VA? I'm not completely sure on that question, but in terms of ICAO, I think ICAO has a limit of 63,000 feet, so flight level 630, and that's the highest that we can put out for volcanic ash. The lowest is surface. We can go down to surface. So if it's a submarine volcano and it's under the water, then we're not really going to put anything out for aviation because the planes aren't flying under sea level. And the highest yet is 63,000 feet. So as we saw, the Hunga Tonga eruption went much higher than that, but we were limited to, 63,000 feet, even though it was much, much higher. So we kind of had to go with as best we could. Next one is, from your experience, does each mountain have a different RGB recipe? No, normally we use the same RGB recipe for all volcanoes, because volcanic ash is kind of the same from all of them. So the separation between volcanic ash and ice and water will be the same. But using multiple RGB images, visible imagery, near infrared, as many different bands as you can. There was MS and a few others as well that were shown. Definitely using those will the detection. And then the last one is, for current detection, is there near real-time support? Because we know that polar satellites are not near real-time detection. So that's why we use Himawari 9 for the current detection, because you're right, polar orbiting satellites are not real-time. They usually come in hours after. So Himawari 9 is the better satellite to use. We just use the polar orbiters as confirmation later on about an event, or verification is another good way of using the satellite imagery from the polar orbiters. So thank you for those questions.
Right, thanks a lot. That's very complete
Scrolling down to the
answers.
next one. So the next one,
It's from Jakarta WO.
hang on, I'll just go back to. Yep. Yeah, there we go. If we use lightning data as our supporting tool, how can we separate CB signal and the ash signal? Is that another way for us in tropical area to determine VA while high convection cloud covering top of mountain? So this is why lightning data is a supporting tool, but it's not going to be your primary method for detecting a volcanic ash cloud, because there is a lot of confusion with CB signal and a volcanic ash eruption. In those examples that I showed, the Hunga Tonga event, there was hundreds of thousands of lightning strikes. You don't get that in a typical thunderstorm. The Uluwun eruption had a lot less lightning strikes, but it was stationary over the volcano, because that eruption went for, I think it erupted multiple times. So that activity would have been over the volcano for a good 8 hours, 10 hours, and that lightning would have been stationary over the volcano. That's another way. If the eruption is short, so maybe it goes for an hour, lightning data is very difficult to use as a supporting tool. It's mostly for those long-lived eruptions. So that we try to only use it for, I guess, the longer eruptions, because sometimes it's just confusing to separate that from normal CB signals, especially in that Ghana imagery I showed in IR that was only there 30 minutes. Lightning would not have helped separate that from the thunderstorms in the area. So you have to really pick and choose your cases, and that's why it's only a support. It's not, not a primary thing. So, primary is satellite imagery, and we try and use lightning to support it if it's possible.
Right. So do you want to move to the next question then? From Ahmad Saputra?
Yep. Is it possible to apply the method of detecting volcanic ash in detecting forest fire smoke, and are there advantages and disadvantages to this method? So yes, sometimes smoke can actually give you a bit of a signature on some of your false color RGB images. They can actually, depending on looking at gases, you can actually detect smoke and everything from some of the RGB imagery that you have. So obviously not just thermal anomalies, but it can be used to detect fires as well, especially on visible imagery. So if it's a fire, it might have a similar looking kind of plume to it. It's anchored to that forest fire or that spot. And you can then track that, especially if you know the volcano is not erupting or it's not near a volcano. But I know a case for Chevaluch with VAC, one of the VACs, they were trying to compare the ash signal, but it was getting interfered with by smoke signals from fires that they were having in their area. So they do give sometimes very similar signatures. So you can use similar methods for detecting both. And I know that is done in a few areas that they use very similar imagery to track smoke movement. So next question is from MWO Ujang Padang. We have, so does VAC could be able to add an alarm or a sound to your website for VA advisory if VAC release a new advisory? So that's a difficult one. We don't have a lot of control. I know they're redoing the web pages. The primary method for getting the volcanic ash advisory is through AFTN. I don't think they can put a sound to the web page, but the web page does refresh every so often, so it will pop up with new products. So unfortunately, I don't think there's much I can do with that one. Did the VAC verify the forecast of volcanic ash dispersion model in their advisory with the results of satellite imagery? So yes, we do. It's an ongoing effort to continue to verify the forecasts using with our dispersion models compared to what's on satellite imagery. Now that we've got a new system, the dispersion ensemble prediction system, we're trying to compare it to large eruptions to try and verify the dispersion that the system provides. And that's always going to be an ongoing effort. So we try and do that. We do case studies based on eruptions. The clearer the condition, the better it is for verification. If it's cloudy conditions, sometimes your verification is very difficult, but you do the best you can.
Thanks a lot, Jared. And if I understood it correctly, you have to jump to another meeting at 3 UTC, right?
I think the next question.
Jared? Jared, can you hear me?
Yes.
Okay, so if I understood correctly, you have to move to another meeting at 3 UTC, right?
No, I can stick around for a little bit.
Okay, cool. Then is it okay to move with the next question that is addressed to Mr. Kentaro?
Yep.
Okay, so the next question is for Kentaro. So somebody's excited with the clear air turbulence method implementation of the Himari 89. And also he's wondering about the determination method of CAT using Himari satellite data.
Okay, so question is, how can you determine cat phenomena? So we try to detect the cat area using the high pass filter or water vapor channel. We detect the wave-like pattern with the short wavelengths, and it is assumed to be related to the turbulence. And this function is originated in US, University of Wisconsin, Madison. Yes, so now, but it's now developing, and we now compare with the product and the actual one. So you're evaluating this product. So yeah, thank you.
Okay, thanks a lot. I hope that answers. And the next question is also related to the previous one. So MWO Jung Pandang, they ask, does this CAT product development could represent the equatorial area?
Okay, so I think so, but I will confirm it to the satellite product developers. Actually, so I couldn't say I'm not. I don't have much information about this product, so yeah, I will answer later after the meeting. Yeah.
Sure, thanks a lot. I can also inform the MWO Jung Pandang once I receive your answer. Thanks a lot, Kentaro.
Okay.
And I will go to the next question from Yolanda. The question is addressed to Jared. How NIR is able to differentiate thermal activity on a volcano and bushfires?
So by itself, NIR is unable to determine the difference. It just determines a thermal anomaly or thermal activity, whether it's from the volcano, whether it's from a bushfire. You have to use other information sources as well. Number of times that we, as the VAC, have seen a bushfire on a volcano. So we will ask the ground observatory or in some of our WhatsApp channels, is this volcano erupting? Is there any activity? They'll tell us this volcano, there is no activity, it is quiet. So we can rule out that it's not from the volcano, that it could be a fire. So we have to use other information to help clarify that. So NIR is just good for determining a thermal hotspot.
Okay, thanks a lot. I hope that answers, because the questions comes from Kuala Namu Med Station, which is responsible for the popular Sinabung volcano. So that's really essential information to know. Right. Then the next question is from Jakarta MWO. They have LiDAR to detect the wind shear. And is that also possible to use the LiDAR to detect volcanic ash?
So I think I'm not as familiar with LiDAR at the ground level, but LiDAR will actually it will detect cloud. So if it's close enough to the volcanic ash cloud, so where your LiDAR is close to the eruption, you may be able to see the cloud appearing with your LiDAR detections. I don't think you'd need additional equipment, I believe, because LiDAR is just detecting the cloud in the area. It should be able to detect the volcanic ash. So it'd be good to explore that more as well.
Okay, thanks a lot. I hope that answers Jakarta MWO's question. Now we're moving to a question from Muhammad Arif Munandar. I don't know if you are here, Arif Munandar. Feel free to open your microphone and ask Mr. Kentaro Suboy if you like.
Okay. Sorry.
I'm sorry, but you're muted still.
Okay, thank you for the question. And yes, first one is we detect it as cloud top with high altitude and thick cloud using brightness, temperature, and visible image and so on. But so second and third question is, I think I need to ask satellite center or satellite division colleagues, it will be they will answer more correct answer more than me. So I email after the meeting.
Okay, thank you, Sensei.
Okay, Kentaro, thanks a lot. So that applies for all the 3 questions from Muhammad Arif Mananda, right? Then I think we can move to the next question. Again to Kentaro. Can you give us insight on how reliable satellite imagery utilization, especially for nowcasting for airport station that are located far from the radar site? Okay, knowing that there is a disparity between Japan and the full disk temporal resolution.
So yeah, I'm now checking the question. Yeah, it will take more time to answer it. So maybe it's better to answer after this meeting, so by email, I think.
Okay, that sounds great. And for the participants, I will send the answers from Mr. Kentaro Suboi to your contact points. So feel free to send me your email address in the private message if you can. That will be very appreciated. Right, then, by the way, this online group discussion is broadcasted through our BMKG YouTube channel. So there is also a question from a YouTube viewer to Mr. Kentaro. How the algorithm for the top height cloud and also how to validate the product with the real observational data. Kentaro?
Okay.
Okay. No, that's okay. I was wondering if you found the question right in the chat, or do you need me to elaborate the question?
Yes. So okay. So I will all question I get it and I got it. So I will all question to answer with my colleagues in satellite experts. So after, sorry, so it takes a little time. So after the meeting, I'm sorry for that.
No, that's okay. That's very understandable. We're aviation forecasters, so I can relate to that. And still the same question from the same person regarding the fog accuracy. Maybe in your division there has been some kind of studies about the fog accuracy with satellite.
So sorry. I lost the question. Current. I have to answer.
That's okay. Take your time.
So okay. So I'd like to answer the question. It's for second speaker. Can you tell us how the algorithm for top height cloud, how Himawari satellite estimates the top cloud height? Have you ever validated that product with the real condition? So we calculate cloud top height based on the brightness temperature of infrared channel and JMS numerical weather prediction model, GSM. And also next question is for the fog product. How's the accuracy of fog product? Can you tell us how satellite can distinguish fog in the surface and cloud in the sky? Both of them are forming by the same particle. I think it's difficult to distinguish these two, and we have to check this surface observations. It's yeah. Only satellite is, but I think it's difficult. Okay.
All right. Can we move to the next question, Kantaro, from Anwar Beauty?
Sorry. So we in charge of my office, so it is difficult to answer this question. So it's okay for me to ask our colleagues for satellite. Yeah.
Sure. And I'm sorry that I caused maybe some trouble regarding this, but thanks a lot. Really appreciate it. And
Sorry for that.
okay, so I think I've read all the questions in the chat box. I'm wondering if Jared and Kentaro, whether you have time or not, because I want to open more questions to the participants in case they want to speak it out. Do you have time still, or because we agreed to do it from 1 to 3 UTC, right? And I don't want to bother you any longer. But if you have extra time, I want to ask participants in case they have more questions.
No problem.
Okay. Any question from the floor? Please feel free to raise your hand. You can also speak it out in Indonesian. I can help you pass the question to the speaker. Maybe from my colleagues here. And we also have attendees from meteorological school today. I saw some participants from the meteor school. in case the students have questions. That's also very nice. I hear none. Okay, then if there is no more question, I would like to ask Jared and Kantaro, do you have extra remarks for today's materials that you have provided?
Sorry, what was that? I think my system lagged out.
Okay, no problem. Do you have any additions? Because we have no more questions for today.
No.
Sorry, you were a little bit lagging, Jared. Did you say something? Jared?
Yep. Nothing further from me.
Okay. Right, and from Kantaro, do you have any additional remarks?
Okay, so I couldn't answer your question, all the questions. So, but yeah, anyway, so I will get back to you rest of the questions to answer more in detail. So, so it's a very great pleasure to attend this meeting as speaker. Thank you very much.
So I thank you, Kantaro and Jared, very much for your time. I know you are very busy and you even spared your time to join us with over 300 participants today in the Zoom and more participants in YouTube. So thank you so much. I think I will conclude today's discussion session and I will hand over to the MC. And we hope to see you again. Oh. Okay.
Sorry.
Yeah, Jared, go ahead.
I just wanted to say thank you for the invite and allowing me to participate in this online discussion group. Thank you everyone for the questions. It's been great to see that everyone's been listening and engaging with the presentation, and yeah, I've been happy to present and answer all your questions. If anybody does have anything further they want to ask, then more than happy for them to just email as well. Again, thank you.
Thank you very much. We enjoyed both presentations from you, and we hope to see you in person though, in Indonesia maybe. All right, then I think I will hand over to the MC. Okay.
Okay, thank you, Arsria, and thank you, Charat and Kentaro, for the great discussion and give our great insight about the utilization of satellite data. So, ladies and gentlemen, now that the full agenda is already over, and please allow us to conclude the OGD event for today. And on behalf of the organizer, I would like to sincerely apologize for any errors that may have occurred before the during today's proceedings. Finally, we wish you a great day and success. So, good morning still. No, good morning and good afternoon for you, Gerard. Bye bye.
Anyway, Jared and Kantaro, because many participants requested to have your presentation slides, if that's okay, would you mind to send them to me? And I will pass the PPT slides to the participants later on.
Yeah, okay, I'll send you later.
I'll do the same.
Okay, thanks a lot. That's really helpful.
And for all the participants, the link for the presence you can find in the chat box. You can fill the submit the presentation and not the presentation. The link for the absent. Okay, thank you. Bye bye all, and see you on the next MetbangTalk.
Bye bye.
Thank you very much, Mbak.
Bye-bye everyone. Absensi apa tuh berarti? Oke, Bapak Ibu, terima kasih banyak sudah menghadiri MetbangTalk. Kami akan leave meetingnya. Untuk materi nanti kami akan distribusikan bersamaan dengan sertifikat ya. Jadi mohon untuk mengisikan attendance list yang ada. Untuk mengisikan attendance list yang ada di link. Thank you semuanya. Bye-bye, our colleagues from GMA. Thank you so much for joining.
Thank you, Miss Yumi. Udah, Mas Bambang, udah selesai.
But all the participants are
Iya.
required to
Thank you very much, Mr. Bambang.